Okay, and welcome back, and we continue this week. Free giveaway. This is, as I said before, this is a free giveaway class, right? Full timing analysis of the Lenovo G50 NM-272 right? The Haswell Intel 4th generation CPU, single CPU. All right, so here we have that was the diagram that I drew last in the last segment, and we're going to continue. Alright, so first I explained that this is the JDC JDC in one, right? And it will produce V in, right? After V in coming through this 2P channel MOSFET to produce B plus point, right? At the same time, P2 is produced coming to power the charging IC. At the same time, AC detect is coming, and then it will output RGVN, which is a linear voltage of 6 volts, right? And it will release adapter OK, which is a low level, which is ACPRN signal, and that will produce PAC in signal. So PA signal is produced, then it will conduct these two N channel MOSFET IPQ307B to conduct these two MOSFET to produce our public point voltage or common point voltage, which is B plus, right? From battery, as you can see, adapter cutoff, which is managed by the IO controller, is sent to PQ308B, right? And it is coming to conduct this MOSFET, and the battery will discharge. So this is their battery isolation, and this is a battery isolation MOSFET, and it is coming to produce B plus point, right? This is the common point. So adapter or from battery, the voltage will all come to this place. Okay. All right, so we're gonna continue. So let's go back to our schematic. All right, in this segment we're going to look at the EC standby working condition and the standby working conditions, and then after we'll look at the bridge or the PCH standby working conditions. All right, so here we have the adapter. This is the isolation and protection I explained last class in the last segment. In this chapter we're going to look at EC working conditions. Alright, so the EC gets its supply after the common point is produced. The aim is to produce this voltage, right? The aim is to produce this B plus real voltage. After this B plus real voltage is produced, then 5 volt and 3 volt regulator IC will generate its output standby voltages, right? So in this class we're going to look at the IO controller, right? The KBC or EC, right? Whatever name you want to call it. We're going to look at the working conditions of the IO controller. So normally the first name that I normally type when going for the EC working conditions, I normally use AVCC, right? I hit enter, right? AVCC, right? AVCC, here it is. IO controller. So AVCC, this is the only signal you can find on the board, on the schematic, sorry, which AVCC, and that goes directly to the IO controller. Now this is the IO controller. As you can see, this is a IT8586E AX that indicate that it has an internal software inside. It doesn't have an external BIOS chip like from older machines where you have an external BIOS chip so that the IO controller can read the BIOS, right? But all the program is embedded inside of this chip, so no need to read from an external BIOS chip. As you can see, there is no BIOS chip. Alright, if you look at the Spi Flash Rom, we have an Spi Flash Rom here, chip select, EC chip select signal, signal output, signal clock, signal input, right? Chip select, signal input, signal data input, signal data output, and the clock. This is your SPI bus. It consists of 4 wires, right? So our SPI bus consists of how many? A total of 4 wires, right? So before we get to that, we're going to look at the working conditions of the IO controller. So the AVCC, as you can see, this is the standby voltage for the IO controller, not the main power supply. This is the main power supply, VST-BY, which stands for voltage standby 1. This is the main power supply for the IO controller. As you can see, there are 2 separate supplies, right? There are 2 separate supplies. So this one is coming to here, and this one is coming directly to this 74 pin of the IO controller. So we are going to look at the individual naming conventions. All right, so this is the standby voltage, right? AVCC, right? VST standby phase lock loop, right? And this is powered by, as you can see, 3 volt always, all capacitors close to EC, right? And these are your coupling capacitors. As you can see, plus 3 volt always R, right? Plus 3 volt always R is coming to power these pins of the I/O controller, and that's pins 26, 50, 20, 92, 114, 121, 127. Right, these pins are all powered by this voltage, right? It's 3 volts. See, 3 volt. This is a linear volt. We're going to get to this voltage shortly. As you can see, it's all combined and it's connected. Plus 3 volt always coming through a short connection. This is a short connection, right? It is just a pad. It's not a component, just a pad, and the trace is underneath it, and it's coming directly to these pins, right? As you can see, VCC, this is the core supply of the I/O controller, and this is powered after. As you can see, plus 3 volt. Yes, this is after we have pressed the power button. We have another signal there, which is V core, which is the core well inside of the I/O controller, and it is connected to a 0.1 microfarad, a 0.1 microfarad capacitor to ground, as you can see. And then we have VCC RTC, which is for the VBAT, right? VBAT as another power supply, right? So before our focus is on these two supplies. This is before we turn on, because if these voltages are not coming, then we can't power the laptop because we have no power, right? So these are your main critical voltages, very important voltages when working with the I/O controller. So suppose this voltage is not coming. If this voltage is not coming, then we know that the board will be dead. It can't power. So we will have to trace where this voltage is coming from. So let's see where this voltage is coming from. VCC, this is the first standby voltage that you should check when checking the I/O controller working conditions. As you know, every I/O controller and a typical laptop motherboard, it needs supply, reset, and clock, and reading the program and getting the adapter information. Then it will turn on the 3 volt and 5 volt standby. Alright, so let's go for the first working condition. Plus 3 volt always underscore EC. As you can see, this is 3 volt always EC. Alright, and it is coming through a coil. As you can see, this is a coil. One is connected to supply and one is connected to the ground, as you can see, for EMI filtration. This is a EMI filtration to filter out any unnecessary noise on the circuit, right, that is generated from the PWM output. But remember that there is a filter capacitor normally on the PWM path, on the output PWM, to filter out the ripples and to smooth out the voltage, right? So this is for extra power EMI filtration. Alright, so this 3 volt, as you can see, 3 volt underscore always R is going to power the I/O controller, a VCC pin, right? Alright, so right, this is the AVCC pin. Alright, so this is coming from here, as you can see, and it is coming through this coil, right? So 3 volt always coming through this coil, right, to become and be renamed to plus 3 volt always underscore EC, and that is going to power the AVCC pin. So this voltage, we have to trace where it's coming from, right? Anybody can tell me where this voltage is coming from? This is a very important voltage. This is their standby voltage, and this is coming from our standby PWM IC output. So let's copy this signal and see where it's coming from. Remember, each class is at least an hour and 15 minutes. So I'll do 1 hour and 15 minutes for each segment. Alright, so let's trace this signal to see where it's coming from. Alright, as you can see, the birthplace, this is for the reset. We'll get to that. Clock and data. This is a pull up. Nope, that's not it. 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 Alright, so this voltage is coming. So let's trace again. So from the top we have that one. Alright, pull up. 3 volt always R. Alright, 3 volt always R. Alright, 3 volt always R. And we have one here to ground. Now, as you can see, 3 volt always cards is coming from this signal, 3 volt always. So 3 volt always is this is where it is coming from. After coming through this short pad, it will then rename to become 3 volt plus underscore all plus 3 volt always underscore r, right? And it is being renamed after coming through this short pad here, right? As you can see, the @ sign meaning there's nothing installed. Alright, so that @ sign for the Compal base motherboard, Compal base schematic indicates that the component is not there, just the pad, but underneath it there's a trace, right? So this 3 volt will flow under and to come and to produce and to be renamed to plus 3 volt always underscore r. So this is the signal we're gonna copy, right? So this is our standby voltage, 3 volt always. So let's copy this signal and see where it's coming from. Paste. Alright, so this signal is going to many places, as you can see. Alright, plus 3 volt PCH, that's that. Nope, nope, no. This is the process that you will use when you're tracing out a laptop and tracing the schematic. Right, so you have to go through each voltage, each section, because you don't want to miss anything, because you might skip and then it's already in this section. You might be confused, wondering where is the signal, where is it coming from. Alright, so this is PCH, VCC, RTC, VCC source standby. We'll get to that in the 3rd class. Alright, that's going to VCC deep sleep well, high definition audio, right, to power the screen, touch screen. Alright, this is for run voltage for LAN. Alright, so we go through each individual. So as you can see, this voltage is a common voltage. It goes to so many pages. It goes to many places on the motherboard to power individual circuits. Alright, we're getting there. Alright, that's coming from the the EC page now. And EC, nope. That's not the birthplace. The aim is we want to find the birthplace of this voltage. Where is it generated from originally? Okay, the birthplace. This is run power switch conversion voltages. I'll get to that in the future class. Alright, this is the block timing. Another block. This voltage is a very popular voltage, very common voltage. We call it a common voltage. Nope. Alright. This is the charger page. And let's see. And here it is. So this is the plus 3 volt always. As you can see, this is the birthplace of this voltage. Right, this is it. Alright, so as you can see, this voltage is generated from this this is known as a SY82 06B QNC, and this is one of the new standby regulators. This has an embedded PWM chip inside, so there's no upper and lower MOSFET, as you can see on the outside, right? Only a coil and a chip. So it's a PWM chip that's integrated inside of this chip, right? So let's look at the working conditions of this. Okay, so I have here an image of the pinout of the chip SYB82 06B and B QNC. Alright, so as you can see, this is the pinout. As you can see, you count in the other direction, right? Normally we count counterclockwise. In this chip, you should count clockwise. And as you can see, you have pin number 1, pin number 2, pin number 3, 4, 5, and 6, pin number 7, pin number 8, and 9, which is the ground. Alright, so pin number 1, as you can see, is the enable pin, and this is the turn on pin from the IO controller or whichever signals is produced to turn on this chip. And first we have supply, first we have enable input. This is V in, right? So this is V in, right? Pin number 7 and 8 is in, right? So pin number 8 and 7 we have 19 volts or 11 volts from battery coming in, right? Then we have the turn on signal, right? We have our turn on signal here, right? All right, so that's input, and we have our enable. Then third, when we have enable 2, right, and we have an LDO, and we have an out, and we have a BS, right? So BS, which is the bootstraps, right? This is the bootstraps for the upper MOSFET switching. Remember, the upper MOSFET is have a drive high and a drive, you have a drive low and you have a drive high. So this boost basically boosts the upper MOSFET drive, right, and it can boost it up to 25 volts, right? So this is my PWM class, and I'm teaching PWM. I'll explain the entire characteristics of a pulse width modulation circuit when it comes to the upper side MOSFET, right? The upper MOSFET needs approximately 25 volts at the boost, right? And you should use oscilloscope to measure this waveform. So I will teach you that in PWM class. Okay. Let me just clear the screen here. All right. So as you can see, this chip has an integrated dual MOSFET inside upper and lower MOSFET, and it is switching, right? And it is produced by this pin number 4 out. So this pin number 4 out has a voltage coming out of it, either 5 volt, right? Either 5 volt or 3 volt, right? Either 5 volt or 3 volts coming out of it, and it is used, and as you can see, it is an output pin, right? We have enable, which is an input, right? Enable 2 enables, enable 1, enable 2, which are 2 input pins, and then we have an output of LDO, right? This is an LDO voltage, could be either 5 or it could be 3 volts coming out, 3.3 volts coming out, right? And that's the LDO, low drop out, right? And then after producing LDO and output voltage is okay, then finally it will release a power good signal, right? Normally this power good signal is a pulled up signal by a resistor most times, right? 3 volt coming up, a pull up resistance, right? And it's normally used as a pull up. All right, so let's go to the schematic, and then we will we'll explain. All right, so let's go to the schematic. All right, so the schematic here, as you can see, this chip, it uses the SY8206B QNC, and the output is 3 volt, and we have another one on below which is SY82C QNC, right, and this one is PQNC. So there are slightly difference here. So one is a B and one is A. So the one is B and one is C. So the SY8208C, which is outputting 5 volts always, and the SY8206B QNC is outputting 3 volts. Alright, so as you can see, so it's 2 different voltages coming out. Right, so it's 2 different chips, so you can't swap them. You can't put a 8206C and expect it to work. It won't work, right, because that one outputs 5 volts, and this path is configured to output 3 volts, and you can't put the SY8208B here and expect it to output 5 volt. It won't work, right? I've tried it and it didn't work. All right, so bear that in mind. All right, so let's go for this working conditions. Remember, we are doing the standby today in this class, and the EC standby working conditions. Remember, we are looking at the EC standby, and we're tracing where is this 3 volt, this voltage, the voltage for the EC coming from, right? AVCC. All right, let's go back. AVCC. All right, AVCC, which is the standby voltage for the IO controller, right? And here it is, and it's the IO controller of ITE, which is a IT8586E, which is as an internal software inside. Software is embedded, no external BIOS reading program. All right, so AVCC, as you can see, plus 3 volt always EC, and plus 3 volt always EC, right, is coming from here, as you can see, right? Plus 3 volt always R through this coil, and it is being ramed to plus 3 volt always EC, right? And it is plus 3 volt always, as you can see, oops, Plus 3 volt always, as you can see, is coming from plus 3 volt always, coming through the short pad and then coming to power these pins as a standby, and this is as the main power supply and standby, and this is the main standby. So these are two standby condition power supply for the IO controller. This is the main power supply, but this is after the switch, right? So let's go back to 3 volt always. I'll go down since I already found it. Forgot the page. Oh, well, it's on page 54. Alright, so I'll keep that page in mind. Alright, so let's look at the working conditions of this chip. So as you can see, this chip in physical appearance is the pinout here. Alright, and this is under the chip, the pinout of the chip. Alright, so it's PU904, as you can see. First we have supply, right, and this is coming from B plus. Remember, I've explained this in the last class, how this voltage is generated, and this is 19 volt, right, or from battery it is 11 volt coming from battery. Okay, all right, so this voltage is coming in through this capacitor, and it is coming to pin number 7 and 8 as an input, right, pin number 7 and 8, right, and these voltages are power supply. So if you go back to the picture, pin number 7 and 8, as you can see, is in. Alright, so in, enable 2, right, plus 3V in. So after coming through this pad here, this B plus coming through, right, so after this B plus is coming through this pad, PJ302, it is immediately renamed to plus 3 volt underscore V in, and it's coming to pin number 7, and at the same time another part is coming to pin number 8 as input, right? So this is the process. Alright, so the next thing we need now is the turn on signal. So the turn on signal, as you can see, is coming from EC on. Anybody can tell me who sent this signal? Alright, this signal is coming from our IO controller, or our EC. Alright, the EC is sending this signal, and it is coming through this 0 ohm resistor. Alright, and this 1 mega ohm resistor is not installed, as you can see, not installed. Right, and then it's coming to pin number 1, right, as an input. Right, so it's coming to pin number 1 as an enable, sorry, and that's an input. So pin number 1, as you can see, pin number 1, which is a enable 1. Alright, so when this enable 1 of 3 volt, as remember, when EC on comes through this resistor, it is then renamed to become plus 3 volt underscore always underscore EN, which is enable, right? So that's the turn on voltage, enable voltage. So we get supply, now we have our enable. So immediately what will happen? Anybody will tell me? Alright, so next we have low drop out, LDO 3 volt LP. So this voltage is coming out, right, after getting enable. After the input voltage coming in of 18 or 19 or 11 volts from battery is coming in from this place. It will immediately release an LDO output, and this is an output coming out, right? So this is 3.3 volts coming out of this place right here, right? So this 3.3 volts is of a LDO, low drop voltage, coming off from pin number 5, as you can see, pin number 5, which is an LDO output. All right, so let's go back to the schematic. So this LDO, after this voltage is coming out, this voltage now is coming to power. So let's copy this 3 volt output, because this voltage goes to the IO controller page, so we want to see what purpose does it serve on the IO controller page. Alright, so we go to here, and as you can see on the black diagram here, right, we have our EC, and it is going to the IO controller, as you can see. So let's go to the next supply, next page. Alright, so after coming through, after releasing from pin number 5, it comes through this jumper pad. As you can see, this is a test pad, right, and immediately it is being renamed to plus 3 volt underscore L. So plus 3 volt LP, this is the original name. After coming through this coil, sorry, this pad, it becomes, see, after coming through this pad, it becomes plus 3 volt underscore L. So let's copy this signal and see the whereabouts of this signal. This is a linear voltage, not a PWM voltage, so keep that in mind. Now as you can see, this is going to power the VCC. This is a deep sleep well 3.3, right? it's going to so many places, as you can see, right? AD VDD, this is for the headphone, this is for the analog VDD, this is the analog power supply for the sound card, right? That's in my interface class. I'll explain about the sound card. That's paid videos rather, right? Plus 3 volt L is coming to here. As you can see, plus 3 volt is coming to the IO controller. This linear voltage, sorry. Plus 3 volt L is coming to the IO controller. Standby 0. So this is coming to standby, another standby pin. So up here we have a set of standby. We have standby 1, 2, 3, 4, 5, and we have standby 0. Right. So as you can see, standby 0. This is another standby voltage of linear. Very important. Right, so it is coming through this short pad here, and it is now powering pin number 112, which is the internal name of this IO controller is voltage standby 0. Right, let's check again the whereabouts of the signal. And here it is. As you can see, this plus 3 volt always, plus 3 volt linear is coming to power the rest of the standby pins, as you can see. Right, and these are all your standby pins, voltage standby. Right, and these are to power this is the first working conditions of the IO controller. Right, in some boards you might see VCC1, VST1, depending on the motherboard schematic, then you'll see different name, but it's the same. Right, so it's the same working condition, the naming is the same. Okay, Alvaro Gomez, this is one of my YouTuber, the Chipmaster. Okay, I will be waiting, do not. Alright, I'll reply to your message shortly as I record in this class. Okay, right, so this is the standby. First, next, what's the next working condition? Lazinali. Where is it coming from? Alright, so this is coming from this is our linear voltage. Remember, this is linear voltage, not PW. This is a PWM voltage. Right, this is the PWM voltage. This voltage has not been produced as yet. Remember that. This voltage has not been produced, so it needs linear voltage in order to power the IO controller first, because linear is critical, that is needed to power the EC, so the EC can get its working conditions up and running. Alright, so let's go back to page 54, I believe. Yes. Alright, so enable is out and it's powering the IO controller. What's the next working conditions? Anybody can tell me what's the next working condition of this chip? Now we have supply, we have an LD output. Next we need enable. So the enable is coming from who? This signal. Who's sending this signal? This signal is coming from the IO controller, EC, as I said before, and it's coming to pin number 1. Simple. Right, to turn on this chip. So it gets power. Now it is being told to start, and the IO controller gets this signal. Now in order for this signal to come, many times this fault will happen on a motherboard. If the signal is not coming, then we should check the working conditions immediately after the IO controller. Suppose the signal is not coming, then this voltage will be dead. No voltage out, no output, because it has not been told to turn on. So this chip will be cut off. Right, so you have to pay attention. Right, so this is the output. In order for it to get an output at this coil, so if you measure the voltage at this coil and you get 0 volts, and you get, first you have enable, the 2 inputs, sorry, then you have a low dropout, then you're missing this signal. This signal is not coming, so you should check the working, where is the signal coming from. Alright, so let's check where is it coming from. Alright, so let's copy this signal, and this signal is coming from the IO controller most times, and it is this chip depends on the IO controller for it to work. In some boards, some chips, it's self-generating and it doesn't need the help of the IO controller in order to turn on PWM voltages. Alright, so let's search for this signal. EC on, first one. Alright, as you can see, it is coming from our IO controller, and it's coming through this pin out here, XLP out. Right, XLP out. Right, so this pin is controlled by a software. So the software inside of the IO controller must be satisfied. The power supply must be satisfied. Right, so this is EC on. Now before this signal can be released though, the EC must satisfy its working conditions first. All working conditions must be satisfied. So we have done one part, which is the power supply, right? The next one is reset. As you can see, plus 3 volt always are. This is coming from here. It's coming from this side also. Plus 3 volt always are. This is PWM, but this voltage is not produced as yet, right? So supply, reset, and clock. Remember, those are the three working conditions. But at this time, this EC doesn't have an external crystal. As you can see, there is no it is a source clock. So here is the clock, CK32K. Right, this is the clock pins, but this IO controller use no crystal, so it use source clock. Right, as you can see, it's connected to AC present and EC lead underscore out. So this clock is already embedded inside of this IO controller, and the software is also embedded. Remember, this is the IT8586E IO controller, right? And the software is embedded. As you can see, AX. Right, this is the version of the version of the chip, and it also indicates that it has a software embedded inside of it. All right, so this is the process. This is the characteristics of this IO controller. So there's no clock, so it has supply. So supply is there, two supplies, standby supply. We have this supply, which is coming from our linear. All right. So once it gets at the supply, then it will start. It has its program, its supply. It has its program. It has our internal clock, right? Supply, clock, and it will get the reset signal from a power with mode PWM, as you can see. So EC on is releasing from this IO controller. EC on is coming from this IO controller, and this is generally 3.3 volts coming from the IO controller, right? So this voltage is generally 3.3 volts coming out of the IO controller, right? 3.3 volts, and it is going to power 3 volt and the 3 volt regulator, as you can see here, and it is going to turn on, right? 5 volt always enable. Right, let's go for the 3 volt first. Sorry. Right, EC on. As you can see, here it is. Right, beautiful. So EC on is coming to here, right, and it is coming to power, to turn on the chip, to turn on 3 volt PWM. Right, remember PWM voltage is different from a linear voltage. Right, this is a PWM voltage. Right, this is a linear voltage. Right, this is a linear voltage. This is a switched voltage. This is after the board is being powered on, fully on, S0 state. Remember that. Okay. All right. So this is the process again. So now let me go over to my my diagram designer. All right. So let's alright, so I'm gonna just extend my canvas here, my height. I want it to be about 600, enough space so I can draw my IO controller. Alright, so the next step, so this is the IO controller, and this is our IT, this is UE1. And this is IT8586E. Alright, so and bold. Alright, so this is the IO controller. As you can see, the working conditions of this IO controller. So we have another chip here. This one is PU904. Alright, so just alright. Alright, so we have our in. Oh, let me rename this, sorry. Alright, in. We have enable 2. So this enable 2 is basically enabling the LDO voltages to come out. Enable 2, which literally means to enable the low dropout voltage. I'll show you the data sheet in a few minutes. What does enable 2 means? Okay. And this is coming from our command point here. Coming to the let me zoom. Alright. And alright. Oops. Alright, and those two enable, and we have enable 1. And that's EC, okay. Coming from our IO. Let's get this a little bit thicker, and this one also. Alright, this is a bit annoying. Okay, so where's my arrows? Okay, it's there. Alright. Okay, good. Alright, so we have this is EC on, so let's copy this signal. So B plus, good. Then we have our enable on LDO. Alright, so we have our, so this is so first we have let's go over to our IO controller. Yeah. First we have our standby VCC. Then we have our we'll just use one since all the names are the same, so we'll just use one. And this is coming from linear. And this one is coming from our Vivo DC. Alright, so here it is. Good. Alright, so let's get these a little bit thicker. I didn't remember. This is very annoying. Alright, so that's the first standby. Then we have our Alright, so let's continue tracing. Save. Oops, I didn't copy this one. Oh boy. Let's delete that one. Let's come in here. Alright, so this is our 6th step. Alright. Okay, so let's go back to our official page. Alright, so EC on is going to come to this enable 1 pin, but as I said before, some working conditions must be met. Right, and when the IO controller gets its supply, right, and it gets its reset signal, the reset signal is a PWM voltage. So this 3 volt PWM voltage will come here, and then after the PWM voltage comes through, this resistor, as you can see, it's a 100k resistor, and this is a 1 microfarad capacitor connected to ground. It will come to reset the IO controller as the EC reset, right? So this is an input coming into the IO controller. Signal name, internal name is WRST, and somebody you might see VCC-POR, which stands for VCC power and reset. You might find EC reset, WRST, they're all the same. So this is the reset signal, and this signal is delayed, right? So as you can see, this 3 volt coming through this 100k resistor. This will take so it's resistor, so it's a resistor. So our resistor is multiplied by our capacitor. Right, and that's 100k, which is this resistor, and this is a 1 microfarad capacitor. Right, so that's 100, which is multiplied by 1. So it takes approximately 100 milliseconds for it to generate EC reset. This is a bit long. Normally on most boards we'll see 47 milliseconds for it to generate the EC reset, because it has to delay, because it's a specific, the signal has to be coming in at a specific time. So in order for this signal to come in at a specific time, then you use a resistor capacitor, and it will charge and delay the timing for this voltage to come and reset the IO controller, sorry. Right, so this is a reset signal, so it's called EC reset, WRTC reset. Alright, so this is a reset signal. So let's copy this signal, internal name, paste it on our as you can see, it's coming to our resistor and delete. And this is our 7th step. Alright, so we have supply, reset. Alright, there's no clock. As I said, the clock is embedded inside of the I/O. Then the software is here. So the next signal that is needed is this signal. Alright, this signal is adapter present signal, and this is our AC in signal, and this signal is critical. Oh, sorry, let me just copy the name of the signal. So our AC in signal, before the EC on releases the I/O controller releases EC on signal, it must get the presence of the adapter, right? And this is known as the AC in. So this signal must be present, AC in signal. So let's see where it is. Here it is, AC in. So pin 108, this AC in signal is an input which is coming to the I/O controller, which is approximately 3 volts, 3.2 volts. Remember, we calculated this in the last section. 3.2 volts coming through, right? And it is coming to the AC in pin. So let's copy this. And this is the birthplace. Alright, and that's AC in. Alright, so that's our AC in signal, and that's coming to your, and this is our supply reset clock, adapter detection. Remember, the program is already being read, so we have no program to check because it's internal. The software is inside of the I/O controller. Alright, so that's the 8th step. Right, so PAC in, adapter detection, as you can see. Oh no, we shouldn't have any broken line here. Let me fix this. Oh, sorry. This is my mistake. No dots. What's on there? What's happening? Oops. Alright, and 8th step. Alright, so the adapter detection is coming, then it will immediately release EC on, and this is the 9th step. And then after, it will output a PWM voltage. So let's go back to the 5 volts and 3 volt regular section here, and this is known as LX. Alright, and this is outputting to a coil. I'll just put a coil here just for and my coil is right here, and I'll put it there. I don't have this. I'm having troubles rotating this thing. Let me try again. It's wasting my time. And I will flip it again. Good. And this is our coil. And that will output the fuel always. Let's come over. I'll extend the canvas, don't worry. And this is an output of 3 volt. Oh, so 3 volt always. And this is our PWM output voltage. Let me just extend that. Alright, so that's our PWM output voltage is. Page properties. Extend this out to about 450. Good. Alright, so we have more space. Alright, and this is our 9. Alright, the aim is to get this voltage out. This is our 10th step. This is also our 6th step because it is a linear. Alright, so I'm getting out there. Alright, so this is the timing. So this is the working conditions, and we have successfully completed this part of the I/O controller. So we have our standby, supply, reset. There's an internal crystal for the clock, internal program, supply, reset clock, embedded software that is being read. After this working conditions is okay, then the I/O controller will configure its GPIO pins. So if we go back to this page, or the I/O controller, oh, it's this one. Yes, as you can see, there are some GPIO pins here. So keyboard section will be initialized and configured. As you can see, we have GPD1. All these are GPIO pins. They all have GPIO input output pins, and they will be configured and to do specific functions, right? So this indicates that the I/O controller successfully initialized reading with the working conditions. So the supply is okay, the reset and the GPIO section will be supply, reset and clock. Adapter detection, it will configure its GPIO pins and do its specific functions, as you can see, right? So all these are configured, and the IO controller will start its functions, right? And the EC on is being generated immediately, right? EC on will be generated immediately, right? Let me find it. Yes, EC on pin 111 sorry, will be generated, and it will turn on PWM output 5 volt, 3 volt, and 5 volt, right? So that's the first part. Let's go back to this. All right, so EC on is coming to 5 volt also, and this one is a SY8208 CQNC, right? And it is outputting 5 volts, right? As you can see, 5 volt is being outputted here. All right, and let's go back to the working conditions. I don't have to explain, it's the same. So B plus rail coming in, after coming through this part, it's being renamed to plus 5 or V in, coming to pin number 8. As you see, pin number 8 is an input here, and pin number 7 is LDO. So this is two different chips, because on this pin number 5 is LDO. So there's no way we can swap this chip and interchange them and expect it to work. I've tried it and it didn't work, right? So this is a different chip because this only have one input, and this one has two input of pin number 7 and pin number 8, right? But this one only has one input. As you can see, it's pin number 8. So when this voltage comes to pin number 8 of 19 or 11 volts from out of a battery, then it will immediately release an LDO 5LP, right? So this 5 volt 5LP will be released, and it is being renamed. As you can see, let's look for the renaming. All right, 5 volt LVP. Laz and Ali, where is it? Okay, let's copy the signal then and see where it is being renamed. So let's copy 5 volt LP, VLP, and here, see, 5 volt VLP. So it's not renamed. So only for the 3 volt it has been renamed. As you can see, there's no pad light for the 3 volt here. So this is very crucial to pay attention to, because the signal name will be changed after. So this is where it's coming out of the chip. Then after coming through this part, it is changed. The name is changed to this name. So this is the name that you should look for, not this one. So that's the trick of a schematic. You have to know how to read a schematic diagram. So for a laptop, so this is the main linear voltage. So this is not used. After it stops here. After coming through this part, then it is being renamed to plus 3 volt L. Okay, so that's the linear voltage. For the 5 volt, it stops here. Only if this come this plot, there is no renaming convention for this linear for the 5 volt. Now after the output is okay, there's a pin, this pin, right? And it is coming through a resistor of a 1K, and it is coming through a 0.01 capacitor, as you can see, right? A 0.01 microfarad capacitor, and it's at the same time it's going back to the what? The out pin. Feedback. So this is the feedback pin. So if there's any over voltage or any over current detection on this line, then it has to report back to the chip. So if there's an over current or over voltage, then it will shut off the output of the switching, and there will be no voltage out because you have an over current protection. So that's called over current protection, right? If you when I'm going to show you the data sheet in the next segment, and some of the functions of these pins, and for you to understand clearly, right? So if there's any overcurrent or any short circuit on this path, then it won't output any voltages because you have an overcurrent protection. So there's a short on this coil, so it will cut off the output voltage, right? If you have an over voltage if it's OVP, if there's an over voltage, right? Suppose this chip is outputting too much voltage, then it will report back to the feedback circuit, right? As you can see, right, indicating that there is an over voltage protection, and it will shut off the output also. So on oscilloscope, you'll get a rising edge. So on oscilloscope, you'll get a nice rising edge like this, right, or something like this, right? So that is a normal 3 volt. All right, that's a normal 3.3 volt working condition that is satisfied. If there's any over voltage protection, if there's an over voltage, you'll get something like this on the oscilloscope. That indicates that there's a fault. Most times on other motherboards, there will be a filter capacitor on the outside that is connected to ground. That filter capacitor will be leaking, and it will cause the over voltage protection on the oscilloscope waveform. This is being taught in my PWM class. So I'll teach you all the tricks and nuts and bolts of a PWM and fault finding in 3 volt and 5 volt. This is just a timing section I'm teaching, right? So after this 3 volt okay is okay and there's no over voltage and there's no overcurrent, then it will output what? Power good. This one, pin number 2, output power good, and that's an output pin. And this power good, as you can see, it's known as 3 plus 3 volt underscore V plus 3 volt underscore power good. So let's copy this signal and see where it's going. Alright, so it is going to AL power good, all power good, and it is pulled up. Remember we said that this voltage is normally pulled up, but as you can see, these 2 resistors are not installed, right? These 2 resistors are not installed, right, as you can see. But if you measure, there's a trace underneath it and it will still pull up the voltage, right? And this is renamed to all system power good, always power good, sorry. So let's copy this signal and see where it's going. Alright, this is always power good. Alright, let's copy this signal and see where it's going. Alright, and it's coming from this chip for the system. And let's go to the next one. On okay, both 5 and 3 volt is releasing a power good signal, and it is being renamed to all power good. And here is it, and it is going to turn on error 20 volts. Now this plus 20 volts is generated to turn on our conversion circuit after pressing the power button. This voltage will be needed. If there is any fault with this voltage, then your machine won't power. It may power is down, power is on, power is off in a repeated cycle, or no display. Okay, so this all system power good signal, as you can see, this is 3 volts coming to pull up, and it is coming to this MOSFET. As you can see, PQ302, and it is coming. These are NPN MOSFET. As you can see, it's coming to the gate of this MOSFET. Alright, it's coming to the gate, and after coming to this set, it's become VSP underscore 1 voltage switch. Alright, it's become VSBP underscore 1, and it's coming to the gate of this MOSFET. And at the same time, this MOSFET will conduct. This will be a low voltage, 0 volt, and it's coming to here. This is a P channel MOSFET. Now at the same time, PR1, PR216 and PR217 is becoming a voltage divider, as you can see. Now as you can see, this is a voltage divider, and this is coming to B plus, as you know, which is 19 volt. Right, this will be 0 volt right here will be 0 voltage. So PR216 and PR217 will become a voltage divider. This is 100 kilo ohm and this is 22 kilo ohm resistor. Alright, so let's go for my voltage divider calculator, and let's see how much voltage is coming out of that circuit. Alright, it should be lower than 19 volts because it's a P channel MOSFET, so the voltage at the source should be less than the voltage at the gate. Sorry, the voltage at the gate at the source, the voltage at the gate should be less than the voltage at the source. Okay, so the gate voltage should be lower than the source voltage. Right, so remember, so this is 19 volts coming to the source. As you can see, the diode is reverse bias, so it must be switched. It must be what? It must be switched because the diode, the 19 volt will stop here. This is at the anode, the cathode, sorry. This is the cathode side of the diode. So in order for the voltage to come, it must be this gate voltage. As you can see, the R is on the outside. So this voltage coming through this voltage divider to come and to conduct this P channel MOSFET, and the voltage will conduct and it will pass and become plus VSBP, and then coming through this pad at the same time to become, after coming through this pad, it is now becoming plus 20 volt on plus 24 VSP, and this is 20 volt, right? Well, 19 volt rather, coming from the adapter, as you can see, or 11 volts from the battery, and it is coming to become plus 20 volts VSBC. So if this power good signal is not coming, then your laptop will turn on and then shut off, or powers without display. So this is a critical voltage that you should check. Many times this voltage will miss. Many times this voltage will not be present because due to maybe water damage, or a pad is broken, or there's a fault on the 3.3 volt rail regulator section, and the voltage won't come out. So the power good signal is critical that this voltage comes out, right? So let's copy this signal over to the diagram designer. I think I'm gonna make this chip a little bit longer. Let's go a little bit. Alright, power good. Alright, and that's renamed to output is always power good, and that alright, so we don't want that, sorry, and this one should have none either, and this is always power good. And just get this one. And this is our 11th step. Alright, so we have completed the standby for the I/O controller and the main standby, right? Let's draw 5 volts. Let me just sketch out the 5 volt rail also. Alright. This one is coming from, this is a different one. And we have an in. We have an enable. An LU. We have an LX, which is the phase angle, and we have a power board. Alright, so we have an in, so catch it from this side. And this one start, and we also make it a little thicker. Then enable, coming from EC on. And this one, why this one has a, should have a line. Alright, and that's EC on, and this is 9. It's already labeled, sorry. And then we have the LX, and this is 5 volts always. Oh, we have a coil, sorry. And that's 10 also. And if this forward signal is missing, it can cause that same issue of no display or repeatedly power on and power down. Okay. This one is a 5 volt VLP. This is 6 also. Oops. Okay, and that's it. Alright, and this is the timing. It's getting there, and you should follow this timing. Right, I will give this in paid classes. I will give this timing, right, for reference, so you can follow and with the steps for a specific board. As you can see, this is for the Lenovo G0-70 NM-272 and this is the timing analysis with step-by-step working conditions and different steps in the area you're repairing. So this is the process in which I teach. And I will continue in the next section. I will do the PCH or the single CPU standby voltages and working conditions of the CPU. In the next class, I will give you the data sheet and the documentations of the pinout. I will explain each pinout according to the data sheet and the timing sequence and so forth. Alright, so that's next week. We'll see you again. Okay.